Okay, student. Next we have another topic in your syllabus, which is spectrum of hydrogen atom. Okay, spectrum of hydrogen atom. Now, what is a spectrum means? So first I will define spectrum. Spectrum is basically the arrangement of colors of wavelength of frequency or energy is known as spectrum. Like, we know that sunlight consists of visible light consists of 7 colors. Okay, now if we divide this visible light in order of their color, like if we pass this visible light, okay, this is the visible light coming from a source. This is the source of light. Okay, so a ray of visible light, when it falls on this prism, then after passing through this prism, this light bend and also it split into 7 colors. So the arrangement of these colors, like we have 7 colors here, 1 2 3 4 5, we have 6 and 7. So this is called a spectrum, because here the light is arranged in terms of their color. Similarly, we can also arrange this light in terms of their wavelength, or in terms of their frequency, or in terms of their energy. So all this kind of arrangement is called spectrum. Now next we have another term which we will use in the spectrum of hydrogen, which is called series. What is a series means? It is basically a regular sequence of lines in a spectrum. Is known as series. Like we have a sequence of lines, like 20 lines or 30 lines in a spectrum, then that is called series. Now next it comes to the spectrum of hydrogen atom. Okay, now hydrogen gas, if we, let's suppose we have a container which is filled with hydrogen gas. We take a system, a container in which we have hydrogen gas, and suppose we heated this gas by using some electric means. Okay, like we heat it by using some electric means. Due to this heating, what will happen? This hydrogen gas goes from its ground state to the excited state. Due to heating, hydrogen gas goes from ground state to excited state. Why? Because we know that suppose we have hydrogen atom, there is only one electron which is in the K shell. Okay, this is the K shell. Here we have L, next we have M and N and so on, shells are there. Now if this electron, if electromagnetic radiation falls on this electron, okay, of energy h nu. So here heating means we are giving some energy to this electron. So what will happen? This electron absorb this energy, this electromagnetic radiation, and due to this absorption of this electromagnetic radiation, this electron jump from this K to L shell. So the atoms now move from, or the electrons move from this ground state to the first excited state. Now here we have billions of atoms, and we are continuously providing heating by some electric means. So it means that after heating, all the atoms inside this gas, they got excited. So some of the electron they move from K to L, some of the electron they move from K to M, some of the electron they move from K to N, some of electron they move from K to O, and so on. Okay, so this is basically the meaning of this statement. Due to heating, hydrogen gas goes from ground state to excited state, because all the atoms they got excited. So like in one atom the electron goes from K to L, in the other atom the electron goes from K to M, in the next atom the electron goes from K to N, and so on. Now next, what will happen? As we know that electron cannot stay in excited state for longer time. Like if we have an atoms like hydrogen atoms, and this electron which is in the K shell, once it absorbs some electromagnetic radiation, and suppose it moves to the, suppose we have electromagnetic radiation absorbed by this electron, it moves from this ground state which is K shell to this first excited state which is M shell. Okay, now this electron here cannot stay for a longer time, so it will de-excite. By de-excitation means it will move back from M to K shell. Okay, in a time of, the time taken to be 10 raised to the power minus 8 second. Like in 10 raised to the power minus 8 second, this electron will go back to its ground state. Okay, so it means that the hydrogen gas which is excited, excited from ground states to excited state, this gas cannot stay longer in the excited state. So in a time of 10 raised to the power minus 8 second, this gas goes back to its ground state. So once electron goes back to its ground state, okay, so what will happen? It will emit electromagnetic radiation. Okay, now the emission of radiations from M to K shell is like this. It is different wavelength as compared to the emission of radiation from, due to de-excitation from L to M, sorry, this is the L shell, KLM. Now if electron de-excite from L to K, it is energy h nu 1. Okay, when the same electron, let's suppose it is in the M shell, it de-excite back to K shell, it also emit radiation, but its energy will be h nu 2. The frequency of this radiation, which is nu 2, will be different from this radiation, because here the difference is different. Here the energy will be bigger, here the energy will be smaller. So it means that once this gas which is goes back to its ground state, it emit radiation of all frequencies. So the gas emit radiation of all frequencies. So radiation of all frequencies means we get a spectrum of this radiation. So we get a spectrum which consists of different frequencies. Now, how we will explain the hydrogen spectrum, because we got this spectrum, we have billions, hundreds of lines, many lines in this spectrum. Okay, so suppose we have, this is the spectrum which is coming after de-excitation of this hydrogen atom. So how we can identify this spectrum, or how we can differentiate these different lines? So in the next video, or in this video, I think it's better to do it in this video. Yes. So next we will discuss the spectrum of hydrogen, which consists of how many series. There are basically 5 series in the spectrum of hydrogen atoms. So these series are called, we have different names for each series. So the first name comes in the mind is like lemon series. Lemon series. So basically we draw the energy bands in the atom like this. We have the nucleus, here we have the K shell, we have the L shell, and then we have the M shell, and then we have the N shell, and then we have the O shell, and so on and so on. Okay, this is the K, this is L, this is M, this is N, and so on. We can also plot the same energy diagram like this. This is the K shell. Okay, this is K shell. Here we have the nucleus, we have the K shell, next we have the L shell, next we have the M shell, next we have the N shell, next we have the O shell. For this, the value of the principal quantum number n is equal to 1, for this n is equal to 2, for this n is equal to 3, for this n is equal to 4, for this n is equal to 5, and we have infinite numbers of shell. So next we have like this, and finally these shells overlap with each other, so we cannot distinguish the two shells. Now once electron got excited, let's suppose this electron, which is in the K shell here, which absorb energy, and it goes from this ground state to the, let's say, N shell. Okay, now during de-excitation there are different possibilities for the electron. This electron first can go from here to here, or it can go from here to here also, or it can go from here to here also. So there are different possibilities, like electron can make a transition from this point to this point. Okay, or it can also make a transition from here to here, or it can make a transition from here to here directly. So on the basis of this we differentiate the spectrum. Okay, like the lemon series, this series, I can write it here, this series occurs, when electron jump from higher orbit to first orbit. Like this is the first orbit, this is the second orbit, this is the third orbit, this is the fourth orbit, and so on. So when electron jumps from higher orbit to first orbit, like electron jumps from this orbit to this, or if electron jumps from this 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 to this, or electron jumps from this to this, or electron jumps from this to this, and so on. There are infinite number of orbits. So when electron jumps from higher orbit, outer orbit to first orbit, we get a series which is called Lehman series. This is Lehman series now. Now this series, lies in the, if we observe this, then the wavelength of frequency of this series is in the ultraviolet region. Okay, so these lines, or this series, lies in the ultraviolet region. Now we have a general formula for the spectrum of hydrogenate. I mean, the formula is 1 over lambda is equal to R times 1 over NF square minus 1 over NI square, where R is called Rydberg constant. And its value is 1.09678 into 10 raised to the power minus 7 plus 7 meter inverse per meter. 1.09678 into 10 raised to the power 7, okay, per meter. This is the value of this Rydberg constant. Now electron comes to the final state. For the final state we have N value is 1. Okay, so for this the general formula will be, for the Lehman series, one over lambda, 1 over wavelength, will be equal to R times, we have the final NF, the value of principal quantum number, where N, I and NF are the principal quantum numbers, okay, of the initial and final states. NF is the principal quantum number of the final state, and Ni is the principal quantum number of the initial state. Now initially the electron was here, or it 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 was here, but finally the electron goes to this state for which N is value is 1. So we, for Lehman series, NF value will be 1. Okay, and initial value of the principal quantum number is either 2, 3, 4, 5 and so on. So we can say that Ni is either 2, 3, 4 and so on. So we can write it as like this: 1 over 1 square minus 1 over Ni square. Okay, where Ni is the value which is 2, 3, 4 and so on. Now the next series, I will stop my video here. In the next video I will move to the Balmer series, okay, because the length of this video is almost 20 minutes. Thank you.